We saw that diagonalization of matrices is an important tool in solving many applied problems. Unfortunately, not every matrix is diagonalizable, even over complex numbers. For matrices that are not diagonalizable, we can bring them instead to an upper triangular form. An upper triangular form of a matrix is not unique, and the same matrix can be brought to various upper triangular forms. What we want to prove is to show that for every matrix there exists a special canonical form, which is called Jordan normal form, and any complex matrix can be brought to essentially single canonical Jordan normal form. The Jordan canonical form is a replacement form of matrix diagonalization in case when matrices are not diagonalizable, and this form is used in many applications. The remaining part of this course will be devoted to the proof of the Jordan normal form theorem. And in this lecture, we are going to discuss the statement of this important theorem. Let us formulate this result. Let T be a linear operator on a complex finite dimensional vector space V. So this means that T sends vectors from V to vectors from V. Then there exists a basis of V in which the matrix of T has a block diagonal form with Jordan blocks on the diagonal. Jordan blocks are square matrices of the following type. We have lambdas on the diagonal, zeros below the diagonal. Then we have a string of ones just above lambdas, and then the rest of the matrix is 0. This is how a Jordan block J lambda looks like. Jordan normal form of a given linear operator or a matrix is unique up to permutation of the order of blocks. This means that any given matrix has an essentially unique Jordan normal form. This is how a typical Jordan normal form of a matrix looks like. We have square blocks placed on the diagonal of this matrix and 0 entries outside. Each of the square blocks is a Jordan block, so it will have lambdas on the diagonal and a string of 1 just above the diagonal. Some of the blocks may have size 1 by 1, and in this case we will have just a simple lambda in this 1 by 1 block. The diagonal entries of distinct blocks may be the same or may be distinct, but it will be the same lambda within each block. Diagonal entries of this Jordan normal form are the eigenvalues of our operator. If mu is a root of characteristic polynomial f of lambda with multiplicity m, then mu appears the total of m times on the diagonal of the Jordan normal form. So the characteristic polynomial tells us which lambdas appear on the diagonal of the Jordan normal form, and the multiplicity of each root mu in the characteristic polynomial tells us that what is the sum of sizes of Jordan blocks with that particular eigenvalue mu. Diagonalizable matrices correspond to the case when all Jordan blocks have size 1. If the Jordan normal form of a matrix has at least one Jordan block of size greater than 1, then such a matrix is not diagonalizable. We point out that each Jordan block has a single eigenvector. So we can see that the vector 1, 0, 0, 0 is an eigenvector for J lambda with eigenvalue lambda. And we can see that the eigenspace of J lambda is in fact one-dimensional. If we consider the matrix J lambda minus lambda times identity, so then the diagonal of this matrix will disappear, and we see that the rank of the resulting matrix will be k minus 1, if we assume that this matrix is k by k. Then the nullity of this matrix is equal to 1, which tells us that this matrix has a single eigenvector with eigenvalue lambda, and it's the first basis vector. And we also see that this matrix has a single eigenvalue. In general, this tells us that the Jordan normal form has one eigenvector per Jordan block. The eigenvectors will be basis vectors that correspond to the first column in each Jordan block. Let us list Jordan normal forms for 3 by 3 complex matrices. We start by looking at characteristic polynomials. So this is f of lambda, which is determinant of A minus lambda I. And for 3 by 3 matrices, this will be a cubic polynomial with leading coefficient minus 1. And we know that over complex numbers, any polynomial factors into linear factors. Let us look at all possible factorizations of a characteristic polynomial for 3 by 3 matrices. So we could have case 1. F of lambda is equal to minus lambda 1 times lambda minus lambda 2 times lambda minus lambda 3, where all these lambdas are distinct. Case 2, we could have f of lambda being minus lambda 1 squared times lambda minus lambda 2, where lambda 1 is different from lambda 2. And case 3, f of lambda could be minus lambda 1 to the power of 3. These are 3 possible types of factorization of a cubic polynomial. Let us write down possible Jordan normal forms in each case. In case 1, matrix must be diagonalizable. So we'll have a diagonal matrix with lambda 1, lambda 2, and lambda 3 on the diagonal. So here we recall that if mu is a root of f lambda, so this means that determinant of a minus mu times I is equal to 0. So this matrix has a non-trivial null space, and each vector in this null space will be an eigenvector. So from here we see that we are guaranteed at least one eigenvector with eigenvalue mu. In case 1, we have 3 distinct roots of the characteristic polynomial. This tells us we must have an eigenvector with eigenvalue lambda 1, an eigenvector with eigenvalue lambda 2, and an eigenvector with eigenvalue lambda 3. And we proved that these 3 eigenvectors will be linearly independent because they have distinct eigenvalues. And then we obtain a basis of three-dimensional space that consists of eigenvectors, and so this matrix is diagonalizable. In case 2, we see that we have a 1-by-1 Jordan block that corresponds to eigenvalue lambda 2, and there are 2 possibilities for eigenvalue lambda 1. We could either have a 2-by-2 Jordan block with eigenvalue lambda 1, or 2 single 1-by-1 Jordan blocks with eigenvalue lambda 1. So we could get the following matrices. So in case 2a, we have lambda 1, lambda 1, 1, lambda 2. Or we could have the case 2b, where we have a diagonal matrix, lambda 1, lambda 1, lambda 2, and zeros elsewhere. In case 3, we have 3 possible subcases. So we could have 3a, the following: lambda 1, lambda 1, lambda 1, then 1 here, and zeros elsewhere. So this is a single Jordan block of size 3 with eigenvalue lambda 1. In case 3b, we could have a 2-by-2 Jordan block and a 1-by-1 Jordan block. So we get the matrix lambda 1, 1, 0, 0, lambda 1, 0, 0, 0, lambda 1. So this is the Jordan block decomposition in this case. And the case 3c is the diagonal matrix. Lambda 1, 0, 0, 0, lambda 1, 0, 0, 0, lambda 1. Here we have 3 1-by-1 Jordan blocks. As an exercise, list all possible Jordan normal forms for 4-by-4 matrices. Next, let us prove the Jordan normal form theorem for 2-by-2 matrices. Consider the characteristic polynomial f of lambda, and we know that over complex numbers we can factor this polynomial. So this will be lambda minus lambda 1 times lambda minus lambda 2, where lambda 1 and lambda 2 are complex numbers. Case 1. So suppose lambda 1 is not equal to lambda 2. In this case, the matrix is diagonalizable since for each eigenvalue we have an eigenvector. And since we have two distinct eigenvalues, we will have two linearly independent eigenvectors which will form the basis of our two-dimensional space, and the matrix then will look like lambda 1, 0, 0, lambda 2. The case which is more interesting for us is when lambda 1 is equal to lambda 2. So we assume that f of lambda is equal to lambda minus lambda 1 squared. In this case, we can triangulate the matrix. And we assume that our triangulated matrix looks in the following way. Well, we know that we must have two lambda 1s on the diagonal. So lambda 1, and above the diagonal we will have some scalar c. In case 2a, so if c is equal to 0, then we get that a is diagonal. Let us consider the remaining case 2b, when c is not equal to 0. Let us describe the action of this triangular matrix A on the basis vectors. So let us take v1 to be the first basis vector and v2 to be the second basis vector. Then we see that A times v1 is equal to lambda 1 times v1. So the first basis vector is an eigenvector, and A acting on v2 will be lambda 1 times v2 plus c times v1. We read this from the second column of matrix A. Let us change a basis from our basis v1, v2 to the basis v1 and v2 prime. Here we keep the first basis vector intact, well, because it's already an eigenvector. And we change the second basis vector in the following way. So we just rescale it to 1 over c times v2. And recall that our assumption is that c is not equal to 0. Let us see how our operator acts on the new vector v2 prime. So this will be 1 over c times a applied to v2. And this is 1 over c times lambda 1 v2 plus c times v1. This is equal to lambda 1 times 1 over c v2 plus v1, or lambda 1 times v2 prime plus v1. And we see that in the case 2b, we bring the matrix to the following form. The first basis vector is an eigenvector, so we have the first column is lambda 1, 0, and this is the action on the second basis vector. So here we have lambda 1, and here we have 1. And what we see is that this is precisely 2 by 2 Jordan block. So we see that in 2 by 2 case, we can either bring a 2 by 2 matrix to a diagonal form with equal or unequal eigenvalues on the diagonal, or we can bring it to a 2 by 2 Jordan block with the same eigenvalue on the diagonal. We see that the theory of Jordan normal forms is guaranteed to work over complex numbers, because we require that the characteristic polynomial may be factored into linear factors. Over real numbers, we could have polynomials that do not have such a factorization. If a real matrix has characteristic polynomial that does factor into linear factors, then we can apply Jordan normal form theory, even remaining within the realm of real numbers. If the characteristic polynomial of a real matrix does not factor into linear factors, then we have to step out into complex numbers in order to bring this matrix to the Jordan normal form.